Okay, so let's just forget all of that. Okay, so this is today's date is 19th. And what I want to start with today is to basically say that, or we'll start with what we left yesterday, which is that when you talk about amplification, we necessarily mean power amplification. Okay, that is an important thing. Okay, and maybe we can just write it this way, that nonlinearity is very useful for amplification. Now I am not going to go into those things. We will waste a lot of time thinking about it. Okay, maybe. Okay, I was not able to prove to myself rigorously that yes or no. Okay, so let's just say nonlinearity is very useful. Okay, that's enough for the remit of this course, which is to design an amplifier. We are not doing a theory of circuits course, right? So let's go ahead and just design the amplifier. Right, it makes more sense. All right, then okay. The other thing that okay, just to see, maybe in some very crude way how nonlinearity is useful, just take an amplifier, take a circuit. Okay, say I have an input. Say I have an input x of t, and let me say x of t is some v in sine omega t. Okay, and if I have a y of t, okay, if the system were LTI, then your y of t is essentially proportional to x of t minus some phase, right? So it will essentially become, for example, some v in sine omega t minus phi. Okay. Again, this constant of proportionality we have not really talked about, but depending on your network, you will get something. Okay. But if you really want to be able to get amplification, let me say this block is an X block. Okay. That is, it takes okay, so let me say what x is defined as. So say this x takes two inputs of this capital X. Say it takes some t, x1 of t and some 2 of t. Okay, so to just keep things clear and not again waste too much going into this stuff, so I have just put like one input. Okay, this is not the two-port network, it's just input output. So I take this and say my output here, say, is x1 of t plus x2 of t whole side. Okay, let's assume that this is a nonlinear device that you have, right? And say I make x1 of t as v in sine omega t and x2 of t c. Okay, then if you open this out, what would the output components be? You will get one at, so you will get v in squared sine squared omega t plus you will get dc plus times dc v in sine omega. So you will notice that this whole self basically something at 2 omega, right? Sine squared omega t you can convert into something at 2 omega, and then this thing is this is at omega equal to 0. If you notice here, you do get a signal running at omega, right? And at the same time, the amplitude of output is controlled by magnitude of VDC. Okay. So in some sense, you increase the power of the battery, you are able to push in more power into the signal at omega. Okay. Very crudely, at least it motivates why an or thing may be useful. Okay. So let's just get that, right. As I said, we don't need to worry too much about whether this is, it's not a mathematics, we are not trying to look at it from that view of whether if and only if a cell is non-linear and active, can you make an amplifier, right. I am not able to prove that. So let's not go, it's not required. Okay. So what I'll do instead is to take off from something else we were talking yesterday, and which is actually a discussion on superposition like calculation. Okay. So we discussed earlier that in order to have superposition, what's the requirement on your circuit? Right? Circuit has to be linear. And why is that? So we mentioned that in LT system, for example, if our input is x of t and output of t, actually this need not be LTI, just linear is enough, I think. Okay, again we have to think about whether you really need time invariance or not. Okay, that's not the aim of this. Okay, so if I have x of t and output is y of t, then in a linear system, okay, if I instead of have an x of t, say some x1 of t gave me y1 of t and x2 of t gave me y2 of t, what imply? Some one x1 of t plus alpha 2 x2 of t will give me what? Yeah, it will give you 1 y1 of t plus alpha y2 of t. Correct? So this is your statement of, essentially the statement of superposition, right? So if you had a circuit, right, let me take a simple circuit. Let me say I have some 3 resistors, okay, like that. Then basically you can assume your system is what I have drawn inside the red box. Okay, system is absolutely linear. So if I had this one as V1 of t and this as V2 of t, you know that to analyze this circuit, break it up into 2 situations. One is in one situation I can just short the output, so I can kill V2 of t, I have only V of t, okay, and then I'll have another situation which is the other situation what's the other situation? I will my 1 of t and then I have my V2 of t. I can find all the currents and everything, right, and just add these 2 results, right. So this we have done in great detail in the first course, right. Also your exam had some interesting results on this if the two sources were at different frequencies, how do you apply it, right. So all of you know how to do this, right. So to be more precise, say I am interested in this current, okay, interested in this current, I want to know what that t is, and I can call this as some a of t and then I can call this as b of t, right? And your answer I of t is going to be IA of t plus IB of t. Okay. In all of this, what I required was this block was linear. Okay. So now, if this is not linear, what do you do? Apply superposition. Technically, you shouldn't. Okay. But what I will show is that you can actually do a very cute trick and then look at a nonlinear circuit, not at different times, not different omegas also, but what we have, I think, got an idea for intuitively, and I mentioned it sometimes, that if you have a nonlinear circuit, you first solve for the operating point in some way, right? You either use a computer to solve, or you make some crude approximations like we did for the diode. You make some straight line approximations and you try and find out what the operating point is. About that operating point, you do a small signal nonlinear incremental analysis. Okay, but I only explained that so far as some kind of a recipe. I thought it is actually quite cute to show that indeed is exact. Okay, so we'll just go over that. So ties in nicely with what we did in the last class. Okay, so basically the problem I am now looking at is, because motivate subsequently when I look at the various amplifier topologies, want to bring home the point that whenever we are drawing these small signal networks with dependent sources, right? An amplifier at the end of the day, if I take a voltage dependent voltage source, right, that's a model for an amplifier, right, in some ideal world, right? So I just want to motivate that when we draw those things, those states refer to the incremental world, not the big complete picture. And to drive that point home, let's just do an example. Okay, so let me go back to the same circuit we were working yesterday, but on previous slide, but let me just replace 3 arms, right, with some nonlinearities. Okay, and I'm at 2 sources. Let me not. So the problem that we want to solve actually, right, is the following: that you have this, you have one source with your, let me call that, say, a VA, okay, or not, VA is not a good name, B1, okay. Over that I am going to put another source, one, which is small b1. Similarly, on this side, I can insert a situation where I have a plus V2, and over that I want a small signal, that. Okay, this is the circuit you want to analyze, and I want to show that you can do this in the following way, which is that, maybe I can show that first and then prove it. So you take the first situation, which is to work with the only with the larges, forget about all signal sources, okay, and somehow solve this problem. Yeah, so in a sense that what happens, your sources in the typical amplifier are at DC, okay, and you have something, you can make some very crude approximations for the transistor, right, and actually come up with a solution for the nonlinear for part of the circuit, which is the in practice this is something sometimes called the biasing circuit. Okay, so you somehow solve it. We'll see in subsequent classes how we can solve some of some special cases of these things, and this gives the operating point. Was another word, operating point, right? All of you are aware, we did this, right? QUI, finish the spelling. S quiescent, right? And what do you do about this quiescent point? You can calculate incremental parameter. So this quiescent point is sometimes called the Q point. Okay, so it's not charge. So basically, this quiescent will give you, for example, some voltage. So I'll just them as some V. Okay, and if the voltage is measured somewhere, some Vx, and I'm just going to put that as a Q. Okay. Similarly, you will have Ix and Q. By X, I mean that it's voltage in this circuit. Okay, the Q is the quiescent. So basically, you calculate the increment parameters at this Q point. Right. So, for example, you might want to linearize these various nonlinear blocks. Okay, and you do all that, or you can find out the Y parameter network that you do at the quiescent point. And then, so that's your step 1, right? And then in step 2, you basically replace the elements, right, which are the nonlinear elements, by some linear versions of them. So they could be, for example, some resistors. And you then work only the small signal circuit. Right. So the values of these resistors, so let me call them, I'm not, so, whatever is inside this, let me call that as some Rx, right, some resistor, each of these, I'm just talking about them in general, right. This Rx is small signal, weak signal is okay, but I think it's more accurately called the incremental resistance. Okay. So basically, if in this particular circuit you had a current flowing through some device, and that current was, say, let me say this element is element A. So if this current was I capital A plus small I small a in response to capital V1 and this small v1, right? Then can you tell me what is the current flow of this block? This I capital A, and the current flowing in this one I. Okay, so you do these two, and you basically alter. So that is very similar to the superposition part, correct? But in superposition part, you use the fact that your circuit was linear to motivate everything. Here I am telling you that the elements are non-linear, right? I know that all these elements I am saying, right, are non-linear. However, this does work, and it is exact. It is not a very crude approximation. Okay, it's not. It's an approximation in as much as saying that you are going to find the for example, if there is a curve, you are going to find its slope and then take its slope resistance. Okay, that approximation is there, but beyond that there is no approximation. Okay, and just we'll see how that comes. So that's what I want to prove in the next few minutes. All right. Let's just, any questions so far? Are you clear? Are you even clear as to what I'm doing? Yes. Oh, good point. So say, so the question is, how do you basically replace the nonlinear resistance by some equivalent increment value? Okay, there are two ways of doing it. One is, if you just go with the, if you were to look at as some kind of two-port network, right? If you look at this entire thing, what we have drawn, this circuit, right? If I wave my hand in the air, you are not going to see anything. If I take that circuit and view it as a two-port network in the following way, right? So I can go just going back. So if I have this two-port network, right? So the entire thing is inside a box, and I don't know anything about that, but I know it's non-linear, right? Then okay, if I just in general define this voltage Okay, now bad nomenclature. So what define this voltage as? Let me call this voltage as some V, okay, VI, okay, input, and let me call as VO, this is the output, this thing, right? And say my currents are similarly I, and okay, this is bad nomenclature. Let me just, okay, I'm not even worried whether these are the small signal currents or the bias currents or anything, just some currents, some voltage, just to convey something to you, right? So it's a nonlinear network, right? So the nonlinear network, you might be able to write this as saying that okay, I think let's drop that and go to the normal we are used to. Let me call that as I1, V1, I2 and V2. Okay, but this is not, it is not this voltage, right? It's just some voltage I am drawing at the input of the port. Okay. So let me just say that I1, for example, is some F1 V1 V2, and I2 some F2 times V1 V2. Okay, we have seen this earlier, right? Previous semester also we have seen this. For depending on whether this network in red, if it's a bipolar junction transistor, we have actually worked out when you what F1 F2 should be. If it's a MOS transistor, so we have worked out what F1 F2 are, right? So what did you do once you had this F1 and F2? So the problem we are trying to answer is how do you work out what the values of these incremental resistances are going to be, right? That's what we are trying to work out. And I mentioned that there are two ways of doing it. One is you just blindly go via the two-port network route. So you can write, for example, your currents in terms of some voltages, right? Or you might be able to write voltages in terms of something. Then you would go to some other, you will choose one of the other, use the Z parameter matrix. Here you will use what we will see here, you will use the Y parameters. So if you have I1 in terms of F1 and I in terms of F2, you can then write down, for example, that the incremental current I1, right, and the incremental current I2, we have done the class. Can someone tell, right? Sajat, you also are familiar with this, right? So I can write this as dou F1 divided by dou V1, dou F divided, sorry, yeah. This is dou F1 divided by dou 2, dou F2 divided by dou V1, and what is multiplied? V1 and V2, right? So when you work out this thing, what's important to keep in mind? Exactly, sir. So this thing is calculated at, this matrix is calculated at the Q point. And this matrix, what's the name of this matrix? Right? This is your incremental Y matrix, right? Now, given that, if you can calculate this Y matrix, you can go and find out what the value of the resistors should be, right? So here, for example, it is a T kind of connection. So you can work out what the Y parameters of a of this kind of T connection are going to be if they were all linear, and you compare 1:1, and you will be able to find what the values of the cost should be, right? So the question is, I want to go from here to there, right? Only for the small signal, and I want to find out what's the value of various resistors, right? I want to find out what are these values. So I can call them, for example, as if I call this as R something, R alpha, R beta, R gamma, right? You can work out for kind of network of alpha, R beta, R gamma. You can work out the Y parameter should be. This is just a T matrix. We have calculated it earlier also. You will find out what this is, what that is, right? And then you can just compare this and this, and you should be able to find out what these R alpha, beta, R gamma. That's like, that's I think the most systematic way of doing it, right? So you make a connection between that and you should be able to get it. Okay. Many times you don't even need to find out what small r, what r alpha, r beta, r gamma are. If you have the Y matrix, you can just proceed with the Y matrix, right? Or you can proceed with the matrix. Sometimes it's useful to keep this in mind and proceed. Okay. Sorry. I'll figure out a way to automate this. Somehow I haven't yet been able to. If somebody knows how to do it, you can tell me also. Okay, so let's continue, and now let's just do this in a quick way. Okay, so again we start with what I had, which is basically I have some like that, right? And let me now take, just for definiteness, let me just put everything precisely. So let me say that that is V capital A, and then, or let me say that is V, let me say that is V1, let me say that is V2, okay, and let us work out, let me make some, let me say that is VA, and through that is IA, right, through this, let this be IB with a voltage plus minus also VB, current through this thing, let it be I with voltages plus minus V, okay. Nothing fancy so far, right? So now when I have the increment, when I include both the sources, I am going to have this circuit, which is I have that, we have drawn this again, but just for everything clear. Sorry, not VA. I want to keep putting that as VA. Okay, that is capital V versus small V1, capital V, small V2. Okay, you note that I write a small V's with a nice wiggle on the tail, right? Okay, so this similarly, this voltage, what will this voltage change to? That will become VA plus small V, small a, right? And this voltage would become VC capital plus small v small c, and that would be VB plus small v, right? Similarly, you can have the current, right? Currents will also change. That would be I capital C plus I small c. That here is going to be I capital B plus I current here would be IK plus I small a. Okay, nothing. This is just nomenclature. So the first thing I am going to do is something that we have all done before, which is apply the substitution theorem. Okay, what does substitution theorem say? Any element across which there is a voltage drop of Vx and current through it is Ix can either be replaced with a voltage source of Vx or a current source of Ix, right? So these elements, these non-linear elements which are here, right? The way non-linear elements that I have here, I am going to replace them by voltage sources. Right? There is no harm in that, right? So So I can just replace that. So that will remain V1. Okay, this is going to be painful to draw, but anyway, right? So this would be a minus plus, and that voltage would be V cap A plus small va. Right? Then I'm going to have another voltage plus minus. Let me call that as V cap B plus small v. Just keep the fact that the directions should be correct, right? Yeah. Huh? What? VA polarity is wrong, correct. Other polarities are correct, right? No, because the substitution theorem says that if you take this element, take the element A, across it the voltage is something. I just replace that element with this voltage source of the same value. As far as circuit is concerned, it doesn't care. It will be. Go back and check the proof of substitution theorem we did in the first course. Okay, that's the substitution theorem. It's a powerful theorem, right? It says that if you replace it like that, you have not any change to the network. Okay, so if you have forgotten proof, go and look at Nagendra's. We don't have recorded lectures for that course yet, so you can go and look at Professor Nagendra's lectures on substitution theorem, right? Or Shanti Pawar. We have one of those from IIT Madras. They record every semester, right? So you can find the proof there. All right. So this is straightforward, right? We just apply the substitution theorem. Okay. So the other thing which okay, maybe I got to write here. For this particular circuit, can you tell me what Kirchhoff's voltage laws and current laws mean? KVL for this circuit basically says that V1 minus VA, right, minus VB is 0, and V2 VC minus V equal to 0, right? And Kirchhoff's law says that VA is equal to IB plus I, right? Those things are clear for this circuit. All right. So I'm going to do a trick which I didn't do actually in the first course. It's there. It was there in Hate. It's moving a source through one. Okay. This means is, if I have, for example, some connection like this, some node, okay, and say have some voltage source here. This is identical to, you move that same voltage source here and there and have it this way. We just, no, I didn't do it. You might have in the textbook. Okay, it's maybe. Okay, it's fairly straightforward because you see what's happening. So if if you were to go loop like this, right? If you were to go that, what would your drop be? Whatever this voltage, right? You go in the same loop, you'll get the same drop. Correct? Then you go in this loop here, what is the drop? 0. You go in this here, what is the, right? Then you try this and you try it here. Right? So for all practical purposes, if you were to consider these 3 points I have drawn as points, right? Everything is identical inside there. Correct? So this is called moving a source through node. We did not do this explicitly in the course, but it's quite fairly obvious. So what I am going to do is move this particular across that node. Okay. So what will, so it would be plus minus V1. I will have a small V1 here, right? And then I have plus minus VA plus small VA, and then we'll have this just the polarity effect, right? That would be V plus, no, don't move the small VB part, just move only the capital VB, retain the small VB, right? Let that small VB be there, right? That's a plus minus for the small VB. And here too, I'm going to, how will this thing look? This will be capital, the VB, and then I have plus minus VC, small VC. Why do you think I did this? So you note that from Kirchhoff's laws, right, I have these here. So what does this mean? So if I go in this loop, this V1 minus V capital A and this capital VB, all of them will effectively add to 0, right? So I can remove that, I can move that, and I can move this. It will be this equation, right? V1, VA, capital V, capital A, VB, that is this equation, right? Similarly, if you take the second equation, VB, that VC, and that V2, right? That is this equation. So effectively, your circuit becomes much simpler, right? And I'll end up following, where I will have this small V1 here, then I'm going to have the small VA there, right? And I have the okay, that is plus minus, the small VB here. Sorry, that direction. Just keep track of the directions, right? Just once we reach this, go and work this out on. It's fairly straightforward. Okay, in all of this, got to mention what are the currents flowing here. So, for example, the current flowing through this block is the same thing, right? Capital A plus small a. What's the current flowing here? I capital A plus I small a. We did not do anything with the current part. And the current flowing here is also I capital A plus I small a. Similarly in the other branches. So if you remember where we want to go to, we want to have a circuit which has only the small v's and small i's. So we have to somehow eliminate these capital I's. How do you do that? I used up Kirchhoff's voltage law. So what do I do? So this question also we have done many times earlier, right, in the first course. If I were to take a current source in this direction and I call this current as I capital A, that means I am pulling out IA from this node. Okay. This place here, how is your IB flowing? IB was flowing this way, right? Or sorry, IC was flowing that and IB was flowing this way. This was your I capital B plus IB. This was I capital C plus I small c, right? So to compensate for the I capital E, say I put another current source like that, current flowing in that way, right? Capital C. And this one, I put a current source like, and let me say that this is that way. Have I done anything to this node? Have I done anything to this node? No, right? Because at this, what have I done? I have added IB and IC, taken out IA. And from this particular KVL equation, that is 0. So I haven't done anything to this node. But is this enough? What about the nodes? I am pumping in IA into this node, right? So what should I do? I should remove IA. So here I should put this current source, that IA. What about particular thing? I'm taking out IC from this node. I should add IC into that node. Okay. Now, do I have to worry about this other node here? No, right? Because by construction, if you take this bottom node, here, right? To see what are the red things that I have done. I'm putting in IA and taking out IB and IC, which is also 0 because of this KVL. Okay. Now, once you have this, what are you going to get? What's the advantage? Once I have that, what's the advantage? What does this allow me to do? Telegans theorem. No, to go that far. Telegans theorem is my favorite theorem, but you don't need to go that far. Look at this branch, these two parallel branches. You have a capital IA there, and here you have IA plus small ia, right? Effectively, if you look at these two nodes, this capital IA and that will compensate each other. Similarly for here also, in this branch the same capital IA plus IA was flowing, right? So this will also go, right? Then will go actually, right? So just to be clear, this current was flowing all the way like that, right? So when I cancel this, I can also cancel that. And similarly, you can do it for all those. So effectively, what this will do is what we wanted, that this whole circuit will break down into a circuit with V1 as the excitation, right? VA with a current I, VB with a current E, VC with current IC, and here you will have V2. Correct? So we are almost done. What's the last thing you need to do? See what we have here, right? Yeah, he's got that. So we want to go from, we started with this thing, right? What I've drawn in yellow, and then we have done now that one, right? Go to this. So I have to basically motivate how you get these resistors there. So as Nikhil said, we basically have to do the reverse of the substitution theorem, right? So if I have an element through which voltage is, through which current is I something and voltage is something, right? I can replace that with any other element having the same and right? So I can replace this one with a resistor. Similarly, I can remove this, right, and replace that also with a resistor. And finally, I remove this and replace that resistor. Okay. Only thing to remember is that is A. I defined it as plus minus this way, plus minus and plus minus. And if I were to call this resistor as R sub A, and if I call this as R sub C, and if I call that as R sub B, then how should I define RB and RC? Exactly. It should be VA by A, right? So your RB is VB by IB, and your RC is small IC by, is small v by IC, right? So in going from that to here, you have basically done the bit of the substitution. That's also called the substitution theorem only. No. Substitution theorem works both ways, which is you can substitution theorem basically says if you have an element across which voltage drop is V something, you can replace that with any other element which has the same voltage drop and same current, right? Then there's no problem. So this was a voltage source through which current was I sub A, voltage was V sub A. Replaced it with a resistor whose resistance is such that VA by A is RA, right? So you got what you wanted, right? So basically we have achieved, and with that I can stop, achieved a superposition like okay. So basically everything now can be done with the two port network parameters of the small circuit, right? And that particular let me say it this way, that the small signal equivalent circuit that you are drawing, right, or the incremental circuit that you are drawing, linear circuit, right? it's a linear, and we know how to analyze linear circuits. So basically what you have done is you have taken the situation where you have some nonlinear elements with excited by some large bias voltages over which some small signal voltages is as a biasing circuit, which you have to solve in some intelligent way, right, which includes the nonlinearity. And then the part which is only the incremental circuit, and the incremental circuit is linear, and the incremental circuit can be represented by one of the four two-port network parameters that we know of, either Y, Z, H or G, right. So subsequently we can work with just the two-port incremental, we can work with the two-port